suppose we take 2, so a minus b and then it is multiplied by a minus 2b. If we multiply a minus b 3, then a minus b, a minus 2b, a minus 2 square. So again we simplify it, we get this, and this 1 plus 2 is nothing but 2. So if I put 2 is equal to 1, again this is simple, a minus b square. Just like our differentiation, we have without the limit. So two derivatives mentioned here by this, and we have shown in a for simple function x like this. And two integral is given by this summation form, and there are some quotient rule, product
ये कह
rule
रहे हैं कि
for
क्या बोलते हैं कि
two
प्रेजेंटेशन कौन सी उसमें
derivative.
वो कह रहे हैं कि भाई हम मैं ऐड हुई तो ग्रुप में आप मुझे ग्रुप में ऐड कर रहे हैं तो मुझे
Quotient
पीछे का नहीं
rule.
पता
And as well.
दिनेश
So
दिनेश
based
मिश्रा है
on
उनका
this,
नाम
in the year 1987,
दिनेश मिश्रा
Phillips first introduced the few analog of bursting power.
कौन सी प्रेजेंटेशन
But it was not so popular
आईआईटी
in the
में
year
आईआईटी रांची
1997.
से
Phillips gave a more generalized form of two, more simple form of two bursting powers mentioned in the last.
पूछ नहीं सकते
So there are two
ये
explanation
दिनेश
functions.
मिश्रा करके कोई है ना तो क्या बोलते
And
हैं
this
प्रेजेंटेशन
is
के
two
लिए
beta
पूछा कि इनकी
function
प्रेजेंटेशन कौन से रूम में
and two
कब है
gamma function.
ना ये आईआईटी रांची से
And this is two beta function of second type. Actually, V upon A it is just notation. And for integers, it comes out to be k, t comes out to be 2 n into n minus 1. Because every time 1, 2, 2 square, 2, 2, 2 raised to the power n minus 1. We add the sum, then it multiply the powers, then it comes out.
प्रेजेंटेशन से
We define myself and Eliezer defined two Bhaskara operator in this form.
उसको प्रेजेंटेशन
And for two Bhaskara operator, we have obtained some point-wise convergence, weighted approximation, and some star-shaped function. F function is star-shaped expressed by this equality. And if F is star-shaped, then two Bhaskara operator is also star-shaped. So in the I also defined this few Bhaskara burst in the and found the difference between two terminal and its symmetry case. And some local results were obtained by myself and Pinta. He's from Romania. And this was another result, which is global approximation. And very recently we have done some results on other operator which are defined on the whole real line. So this operator was not discussed earlier. So T and fx is given by this, and T and k and x is the basis which is tan inverse x. So for this, and this is the Gauss stress operator which is well known. So we found So we found that the composition of this operator Tn and Wn Gauss stress, and our kernel comes out to be this. And for this, we have obtained the moments of this of these operators, both operators, and their composition part obtained in the last. And using this, we can find the moments. And after finding the moment, we have obtained some. And we have observed that this, if we take the limits like this, we get post-feeder operator. And this is what the subpart was the stress operator, and this is the composition operator, which is fx in both cases. But one part is converging to post-feeder operator. So modulus of continuity also is defined because it is defined on the whole real line. So there are two forms, this and this. The form is this, which is indicated by double bar, and we obtain this result. And these are some quantity estimates and difference estimate. And finally, we have shown it two graphs for this function x square, which is about 2x. And dot it is the function itself, and these are the operator for different values of x. Another function for this This is the subpart TN, and this is composition operator. So composition operator is if we take this same value 2, so it is far away. Composition is far away from the function. So difference estimate we have also considered very recently in the last 5 6 years. Some difference estimate we have obtained the general result for the difference in two operator UN and TN, and this is the general result. Based on this general result, we have obtained we have shown some quantitative estimates for different operators. This this is the other of difference between Laskopov and SQ operator, and the Zaz and Zaza operator. Different with different bases here. Different bases are means we are considering the UNKX and TNKX. For example, Zaz basis or last support basis, and this may be same. NK and TNK may be same. Maybe FK by N. So for this, also myself and Anna Maria also we have obtained the general result. And, these are some of the books which I have written in approximation theory. All are in approximation. Some books are edited books. That's right. Thank you so much. Any questions? Thank you, sir. No question. I think there is no one who is working in approximation. Yes. Yeah. Actually, Q calculus, Q calculus is not new. It is an old branch in mathematics as well as in physics. But it was introduced in approximation theory in the year 1987. And basically, it was introduced in approximation in 1997. Hmm. Okay. Thank you. Thank you, sir.
अंजुमन का कब है? अंजुमन कब है तुम्हारा? अरे इधर आओ। खाली में तुमको नहीं दूंगा। बापू जी इतना हमारा वेरी क्लोज था। बापू हमारा क्लोज था, हमारा ऐसा था। ये याद है कि बहुत दोस्त थे।
लगा लो उसके बीच में।
School of Mathematical and Statistical Sciences, IIT Mandi, Himachal Pradesh. And we will now review his talk on efficient physics, inform neural networks, to study complex flow problems. Now I invite Professor Rajendra Kumar to deliver his talk.
राजेंद्र कुमार साहब। हो गया
Okay, so yes.
Okay, thank you. First of all, good afternoon all. So myself Rajendra, I am from the School of Mathematical and Statistical Sciences, IIT Mandi. This work is basically done by my student Vishwanath. So the topic is the development of some efficient architecture using physics informed neural networks and its application to unsteady flow problems. So I think nowadays, this spin is very hot topic. Everybody is trying to work on that. Mostly what they are doing, taking some sort of existing method, using their problems and getting some solution and showing the results. But that is not the I can say that way to deal with these things. Spin is is good alternative for solving complex let's say PDEs or fluid flow problems, but it has a lot of limitations. Just started in 2019 I can say, but still it is not up to the mark. Many simple problems cannot be solved properly using physics informed neural network. So I will just give you some idea what is the physics informed neural network, what are the limitations, and what we have come up with some sort of solution to that. So the topics are just motivation. I think many of you know about spin, but I just want to give some idea what it means, how it works, what is the basic architecture, and what we have done. So when I'm that means tell me the word spin. So from where it basically the idea came from. So if you see that the first idea it came from human brain. If I can mimic the work of human brain, basically what neuron does, and that if I can replicate it, the idea, then I can say that this is basically the artificial neural network, which is basically working as, I can say that, abstraction of our human brain system. That is basically. So if I compare with our neuron, so basically if I see it neuron, if I discuss, it has dendrites, it has cell, it has nucleus and axons, and it has some system of steps to follow when I am getting some inputs to output. That means in terms of action. So if I compare that, so the artificial neuron also follows the same type of ideas, not in complex manner. It is very simplified form of our neuron. So first of all, if I check input, that basically considered like a dendrite. Our dendrites, if I can show you, so dendrites means this part. So they are collecting the inputs, and which is basically considered here in our artificial neural network as the input signals coming from this. Then synapse basically I can say that it is called weight function, which is basically giving you so you can see that is this inputs, they have different type of patterns. So some of the this dendrite can take more information, some of them take less. So depending upon that, so some weight function is defined for that. Then if I go for the cell soma, so basically it is pre-activation function or pre-activation. Basically that I am going to add all the weights in that, and finally with some bias, where basically the nucleus what basically does, it basically calculates all the things, that is in terms of activation function, and finally the action, which is basically giving us the output. So basically the concept is same like what a usual neuron does, and the same idea is informed there. So it is for one single neuron, I can say the artificial neural that is neuron. But if I contact let's say one neuron with another one, it is basically called the neural network. And if I take more number of neurons, so what I will be having? I will be having input, then output will be the input of the next neuron. So that means it is basically can make a structure, that is basically we call it as deep neural network, where we have more than one hidden layers. Hidden layers means I can say that I am just connecting one neuron to another one. So the action will be connected with the dendrite of the next neuron, and in this way it can form a that means artificial neural network. So now another important aspect, because my concern here is basically physics informed neural network. So when I am considering that some sort of behavioral aspect, so basically I will be using another type of the important aspect, that is called the supervised learning. Means I have some input data, I know that what is the input, what is the corresponding output. So I have a labeled form of that. Means I know this data, the first part is what is meaning, second part what is meaning. So I can have some sort of mapping with each of the terms. So basically this is I'm just giving a short idea of that. So basically it is called supervised learning, when I have some information which I know that what basically is what is the input or what is the information I am giving and what is corresponding output, or that means that means I'm getting. And using that, if I can use more number of layers, means I can have a system of this type of connections. So I can have a that is called a deep neural network, means a lot of hidden layers, means I have more number of layers. If I have more number of layers, then I will be having more number of parameters, and to train that I need more that information, means more data. But in reality, the problem is that many cases we don't have that huge data, or data is limited due to different reasons. It could be expensive to get the data, or it may be not possible. You have to have the measurements. So that means though people are working deep neural network, artificial intelligence, but they don't the inherent problem is we need huge data set. We have to learn that, it takes huge time to get the result. Whatever we are saying that it is coming within a few seconds, but it takes a lot of time to train the system. So it is not like that I am giving something and I am going to get the output. It is not the case. So that's why though the system gives quite good output, but it takes a lot of time. You need supercomputers, you need huge high performance computing facilities, and those things are, I can say that, the limitation for using in our usual point of view. So what would be the overcome to this, or what would be the solution to this? So the first solution that is there, that is called the physics informed neural network, or PIN. So what is that? So first thing is that what is the importance of these things? So let's say I have limited data. I know some physical phenomena. Okay, the data is coming from a physical phenomena. So I can relate. So let's say my data is limited. So I can take that data along with the physical form, that means relation. That can also give me some sort of input to that, and overall I can get a good result. So that is basically the idea of physics informed neural network. So neural network is what is there. I have to train it. I have to get the output if I have some input there. But that may lead to a non-defined solution or some solution which is not accurate one. So here physics informations in terms of differential equation or any terms of mathematical relation, I can incorporate that. Then a minimum that means information or data can give me a very good result within a very simple computational that means cost. So so the first of this idea was given by Rising in 2019, though they have done this work in 2017, but it published in 2019 in Journal of Computational Physics, and it has shown that the physics informed neural networks are networks that solve supervised learning tasks while also incorporating the laws of physics, and that has not only, so basically that means if I say in terms of this artificial neural network, the thing is that basically it is like I can say that a inverse processing, or I have some input, I am going to do some calculations in terms of activation function, I am going to get output may not be correct or desired solution, my desired accuracy. I will be using the loss function, and I am again going to optimize it, I am going to refine my inputs again, and I am going to get the solution. This is usually the that means artificial intelligence, or you can say the neural network works. Now the problem is, along with that means the loss function in data, if we can also incorporate a loss in the physical loss, it together will give me a loss, total loss, that basically comes through the physics informed neural network. So now not only the data loss along with the physics loss, it will be accommodated together. Then we will check that what is the error coming. If my error is within my required that means tolerance limit, I will say that I have reached my solution, otherwise I have to optimize it. So what would be the general architecture given by Rising is that, let's say I have input, let's say X and T are the inputs, and we have some sort of neural network. It could be some sort of layers, I can say hidden layers. After some calculations, after some this activation function or all these things doing, I am going to get an output UCAP. Now if I want to introduce physics, so basically it is nothing but differential equation. So usually what he did, he basically take the automatic differentiation in the calculation along with the data loss. So he has calculated the physics loss along with the data loss, and totally it is says MSC, means basically I can say that the measure in terms of error for the data loss as well as for the physics. So if I take them together, it will call the loss of this architecture. And if this loss is less than my error, as I told you, I have some tolerance limit. If it is less than that, I reach that. Otherwise, I may take in terms of some epoch. Epoch means how many iterations I am going to calculate, to define my things. So either of them if reached, then I can stop it. Otherwise, so it is done. Otherwise, I have to optimize my whole this error, and I can go to check, because here in the neural network, W and B basically weight function and B is the bias. It has to be calculated. Has to be calculated. So I will be again going to refine them, and again I will do the same process. So it will go still I reach this one, this less than epsilon or greater than the maximum epoch, and we can say that I have reached my solution. So this is the usual architecture. This is called the vanilla model, the basic model that is given by Rising in 2019 in this paper, Journal of Computational Physics. So now here if I see the roadmap from simple basic neural networks up to our pin. So first in 1943 started in the simplest of way, using 0 and 1 this concept. After that in 1957-58 the perceptron idea, means I can take a 2 and I can combine it, so that idea came in terms of, you can say that number of neurons can be added to that. Then a historic improvement was in 1986, the back propagation. That means the loss function can be optimized and I can refine my solution, I can get a better result. So it was basically 1994. That is the basic PD. In 1998, that is more advanced, and we can see that this paper of this paper of this Lagrange, they have shown that yes, OD PD can be very accurately solved by using neural networks. And after that in 2019 this rising, he has shown that if I incorporate the physics also in the architecture, that can give me a very good result within a very small data set. Okay, so that was basically the I can say that the time history of the improvement of the thing. Now if I see, I don't know, it is not coming forward. Anyway, if I see that how pin works, so let's say that I basically there are three type of that means classification I can put it. When I have no data or very small data, but I have lot of physics, so I can use it as a simple PD solving problems for our problem that is called, and it can easily be solved by any usual methods, no problem. If I go for the last one, big data, I have huge data, I can train my model very accurately. It may take some time, lot of computation, but still I can solve the problem as good as the required accuracy without any physics. But problem arises when I have limited data. If I have limited data, none of them is going to be good enough to give me the required accuracy. In that case, pin means using physics also can give me a very nice result. And that is basically in terms of inverse problem, because I am going to first going to, because I have data as well as physics, so I first want to get my the parameters correctly in terms of inverse problem, and then I will solve it. So basically when I have limited data available, as well as I have physics also or physical relation available with me, I can use this one, and which can give me the good result. But again, the problem here is how small data I need, and secondly how much computational cost is required, and is there any problem in the architecture itself. So these are some of the questions. So if I say this way, is the model given by Rice is good enough? It is good enough. At least as I told you, I can solve it PD, let's say a steady state problem, it is fine. But the problem arises when time dependency. If I have my solution is time dependent, basically let's say fluid flow problems, any problem, let's say our financial modeling where time is very important factor. In this case, still pin is not good alternative, because still now no method or no good method was available to capture the time, capturing the time information, time history of any problem. That is one problem. Then another very important problem is that chaotic behavior cannot be captured properly with the pin. Let's for example Lorentz system, if I take small change will give a huge change in the trajectory or the differential, that means differential the solution. Then it is also not possible. Also it is hard for high frequency multi-scale solution. So as I told you, for steady state problem, if you have a slice, you want to say that what is my solution at a particular time, it is fine, no problem. Or let's say some time duration, or my problem is very sensitive with respect to chaotic behavior. Pin is not still good enough. So lot of things or lot of that means refinement is required in the architecture. Another very important problem is vanishing or exploding gradients. So what happens when I'm going to that means do this activation calculations in many layers, I can come up with a vanishing gradient, means gradient is going to be zero. If vanishing is going to be zero, training will not be sufficient, first of all. Secondly, exploding gradient means when gradient is going to be huge in terms of calculative values. Then at that time your training will not be sufficient enough. Not only that, it can lead to a very bad output. That means you have to control this vanishing and exploding gradient. It is not known beforehand. So during the calculation it may come these things. So during calculation I have to be very careful to take care of this vanishing and exploding gradients. And finally, as I told you, data is also very precious many times. For example, let's say if I want to solve turbulent flow model or turbulent flow or any problem which is not easy to get the supervised data, or very much difficult to in terms of this financial point of view, then also I have to very careful about minimum data can be used, but our results should not be tempered due to that. So these are some of the problems usually still there in pin. So what would be the solution to that? So we come up with two set of architectures. I am going to discuss in the next slide. What we basically our interest, I want to make a time dependent capturing mechanism in my pin. First one. Second one is this vanishing and exploding gradient should be captured. That is another issue. Should be done and limited. As much small data I can use, that is my next target. If I use less data, obviously my computational cost will be less. So these are some of the things. So first, architecture we have proposed, that is basically we have given the name as this wavelet, okay, physics informed residual neural network, or WPIRNS. What is the meaning of that? So basically here we have taken activation function in terms of customize. We are basically showing it customized wavelet function. It is not wavelet function, but we have taken basically W1 sin t, W2 cos t, something like a periodic point of view, so that the capturing of time dependency or periodic nature of the flow can be captured. So that is the first incorporation from our side, activation function. To capture the to avoid the gradient loss or exponent gradient, we have used residual neural network, so that where I have I have been that means having this gradient 0 or gradient going to be exponential, we will be basically taking that as an unit. Basically we are keeping that. We are not going to calculate that training part. We will be basically not considering that that layer, and we are going to the next layer without incorporating anything. So that is basically I am just going to pass that layer without doing any calculation. So this is basically something. And also in this architecture, when we are going to use it, we have used very few data points to calculate my things. I will show that the architecture. And second one is another thing. Here we have considered as different framework, that is called physics formal. The idea here is, because when I am considering time dependency, so it is better to take the sequential time in my training data. Usually what happens in PN, we are using discrete points. So discrete points may lead to not capturing the previous value. So that's why physics format, or you can say the attention based idea, it is basically what it does is basically take the sequential time data as an input, and ultimately using encoding decoding this concept, basically it will give us it will basically take the all sequential time data for different time levels. That is one thing. And again, using this thing, we also this handle this gradient loss as well as the gradient exponent gradient this situation. So these are the two formula. Here we have not used wavelet. Here we have used simple weighted 10 function as my activation function. And overall, these two methods, and the best thing of this physics format is that it is very fast. So one was very less number of grid points is required, or that unknown values are required. Second one, very less computational cost is required. I will come to that both. So now come to the first architecture, that is W.
Dr. Rajendra, sorry to interrupt you. You go to the previous slide. Just curiosity.
Yes.
Long time dependence. And which type of activation function you will use?
For which one? This
long time dependence.
Long time dependence, that's what I'm telling. If I use physics format, basically here we are taking sequential, a time sequential. Basically, let's say I will show that I have, let's say, data from 0 to 19 seconds. So each of the slice, let's say I have a slice of 0.1 second. So I am going to take all time, is 200 slices in sequentially. So time, let's say t is equal to 0, t is equal to 1, t is equal to 0.1, 0.2 in this way up to 19.9.
No, my query is if you just can use the activation function like Gaussian type.
Actually, Gaussian type and other things will not capture the sequence. We have done this. This is not going to work. The thing is that for the first case, what I told you. So here, this activation function of terms of wavelet basically is good for inverse, capturing inverse, inverse data. This is not exactly wavelet, but it is customized wavelet. Basically, sequence this periodic nature of that is going to help us in capturing the.
But you know, just my query.
Yes.
If you take the wavelet transform, I do not have idea, but if you take the Fourier transform of the Gaussian, that gives the Gaussian.
Exactly, but that is good for steady state. That's what I'm telling. Gaussian, or if you take Fourier, they are very good for steady state. Let's say I want to calculate also. I want to calculate, let's say, for a particular time point. I have the data. Let's say mu few data. I am just want to calculate a particular point. No problem. But I have, let's say, 0 to 19.9, and I want to take very few data in each slides. Each slices. Let's say, as I told you, 0.1 means I will be having 200 slices. And I want to take very small data from each of the time step, and I want to calculate the full. I want to show my my time dependent flow from 0 to 19.
Here also size of the sample is less.
Very less. I am coming to that.
And at the same time, you have to ensure that physical loss will not be
there.
Yes.
Along with that, it should give me the full okay, full 200, okay, this slice what I am saying. Challenging. It is not possible. Children, that is the first method. As per our knowledge, is the first model we have developed architecture. So what the idea is? Idea, as I told you. Another important thing is that when I am going to solve let's say fluid flow problems, I have UV and pressure basically, right? So we are not using pressure also, just to take care of less number of points. We will be velocity profile, velocities, and also we have first time we have also calculated stream function vorticity from this calculation. So that is also the first time we have used UV to calculate, to capture the pressure as well as vorticity and stream functions. Okay, so overall the architecture is very same. Only our this activation function we have changed here. So we are going to get after the same thing. Okay, here you can see that due to the residual network, this identity X will be there, where in which layer I have, let's say, the gradient loss or gradient exponent gradient. So that layer will be skipped at that time. So each time it may be different layer, but we are basically going to capture that, and we are going to skip or going to skip that layer. After that we are going to get UV and P. So UV and P we are going to calculate. We are only giving the U and V. So X, Y and T are my inputs only in terms of U and V, but I am going to get U, V and P both as the output. Then we are going to do this automatic differentiation just to calculate it easily, and then we are going to get the error from this our Navier equation, since the U, V and the continuity equation. And along with that, the first one will be my loss in data. Means I have, let's say, initial and boundary data. So that data will be calculated as a data loss, and physics loss will be calculated using this our that means momentum, V momentum, and the continuity equation. Overall, when I am calculating that, I can have the total loss here. Okay, this is total loss, and if this total loss is basically satisfy the stopping criteria, as I told you, it could be your error. We have taken a 10 to the power -6 is my error. Okay, or you can have 20,000. We have taken only 2,000 epochs, so that I am coming to that. So any of them, if it is satisfying, I will be solving. I will be stopping my this result.